Dear friends, yesterday's class we studied two important theorems. One is the shifting theorem, another one is theorem which can be used to find the Laplace transform of periodic function. The shifting theorem states that if Laplace transform of if Laplace transform of f of t into u of t is defined as f of s, then Laplace transform of the shifted function f of t minus a u of t minus a is given by e power minus as f of s. This is called as shifting theorem. And we have also seen the theorem or the rule which can be used to find the Laplace transform of periodic function. If you have a periodic function f of t with time period t, and if f1 is the function describing the first cycle of the periodic function, and if Laplace transform of the first cycle, Laplace transform of f1 of t is f1 of s, then Laplace transform of the periodic function f of t is given by 1 by 1 minus e power minus ts times the Laplace transform of first cycle. With this background, let us see how to find the Laplace transform of a rectangular wave with a time period 2t. See here in this figure is a waveform, rectangular wave whose time period is 2t. 2t is the time period of this wave. It is a periodic wave which continues in this fashion. Now, the period is 1, that is a part of the waveform which repeats itself. So, if I just draw the first cycle of the waveform, I have just drawn the first cycle of the waveform. First cycle of the waveform has a magnitude of 1 between the time interval 0 to t, it has a magnitude of minus 1 between the time interval 0 to 2t, and it has a 0 value for time t greater than 2t. So, now let us see how to write the function, how to write the equation for first cycle of this periodic waveform. This first cycle of the periodic waveform can be synthesized by having a unit step function that is u of t, and at t is equal to capital T, at this time interval, I can add a step function having a magnitude of minus 2. If I have a magnitude of minus 2 till 0 to t, the magnitude of function is 1. Afterwards, I am adding another step function whose magnitude is minus 2. So, one function has a magnitude 1, another function has a magnitude minus 2. If I add these two functions, the resultant function will have a magnitude of minus 1, that is what plus 1. If I add minus 2, plus 1 minus 2 becomes minus 1, the function continues like this. So, if I have just u of t minus 2 times u of t minus t, the resultant function will have a magnitude of 1 up to this point, and will have a magnitude of minus 1 beyond this point. But now my aim is to make this value 0, make the magnitude of the function 0 at 2t, at t is equal to 2t. So, to make this function 2t, now the function magnitude is minus 1. If I add another step function whose magnitude is plus 1 at this point, the resultant magnitude will become 0. So, first I need to have a step input of magnitude 1, or I need unit step input. Then at time t is equal to t, I need to have a step input whose magnitude is 2, and again at time t is equal to 2t, I need to have a step input of magnitude 1. So, if you write the equation for the first cycle of this waveform, you can write f1 of t as u of t minus 2 times u of t minus t plus u of t minus 2t. So, sum of these three step functions results in a waveform like this. That is the function which describes the first cycle of your waveform. Now, once I know the equation for first cycle of the waveform, which I define as f1 of t, the original waveform can be written as first cycle, and the same first cycle shifted in time by 2t, so that you get the second cycle, and same first cycle shifted in time by 4t, which gives you the third cycle, and so on. So, f of t can be written as f1 of t plus f1 of t minus 2t into u of t minus 2t plus f1 of t minus 4t u of t minus 4t, etc. Now, using periodic theorem, we know the Laplace transform of this function can be obtained by multiplying Laplace transform of f1 of t into 1 divided by 1 minus e power ts, where t is a time period, but in this case the time period is not ts, it is time period is not t, it is 2t. So, if I take Laplace transform of f1 of t, that is Laplace transform of first cycle, you remember it has a unit step function, then minus of a delayed step function with magnitude 2 plus another delayed step function which is delayed by time 2t with unit magnitude. So, Laplace transform of f1 of t, which is denoted by f1 of s, is equal to 1 by s minus 2 by s into e power minus ts plus 1 by s into e power minus 2ts. So, this is the Laplace transform of first cycle or one cycle of our periodic wave. Once you know the Laplace transform of one cycle of the periodic wave, you can easily find the Laplace transform of the original function, that is the periodic function. So, Laplace transform of f of t is 1 by 1 minus e power the time period times s, that is 1 by 1 minus e power minus 2ts multiplied by Laplace transform of the first cycle. So, the Laplace transform of the final periodic function L of f of t is 1 by 1 minus e power minus 2ts into 1 by s minus 2 by s into e power minus ts plus 1 by s into e power minus 2ts. So, this is the Laplace transform of the function under consideration, or this is the Laplace transform of this particular waveform. Now, once you get this Laplace transform, you can make some mathematical manipulations and simplify this function. If you look at this function, this denominator, the denominator can be viewed as 1 square minus e power minus ts whole square. This e power minus 2ts can be viewed as e power minus ts whole square. So, this function I can realize in the form 1 square minus e power minus ts whole square. So, this denominator, that is 1 minus e power minus 2ts, can be written as 1 minus e power minus ts multiplied by 1 plus e power minus ts. And if you look at the numerator, or if you look at this term, s is common in all these terms. In the denominator, the term s appears, so we can take out s outside, this 1 by s you can take it out. And after taking this 1 by s out, if you will just look at the numerator terms, I can realize these terms, one as 1 square and this term as e power minus ts whole square, and this term as 2 into 1 into e power minus ts. Or if I combine all these terms, this is of the form 1 square plus e power minus ts whole square minus 2 e power minus ts, which is of the form a square plus b square plus b square minus 2ab form. So, I can write this term as a minus b whole square, or 1 minus e power minus ts whole square. So, if you simplify this function, it is 1 by s into 1 minus e power minus ts whole square divided by 1 minus e power minus ts into 1 plus e power minus ts. So, simplifying this, cancelling out these two terms, so we can write the Laplace transform of this periodic function as 1 by s into 1 minus e power minus ts divided by 1 plus e power minus ts. So, this is the Laplace transform of the square wave of rectangular wave of magnitude 1 and time period 2t. Now, let us take another example. Here the problem given is, show that the transform of the square wave shown in figure is 1 by s into 1 plus e power minus as. So, aim is to prove that the Laplace transform of this function is 1 by s into 1 plus e power minus as. Let us see how to do it. It is a very simple problem. Now, it is a periodic wave whose time period is 2a. If you see, this function has a magnitude 1, then it becomes 0. From 0 to a, the function value is 1, and from a to 2a, the function value is 0. So, this is one period of your waveform, one period of your periodic waveform. So, the period, this time period of this waveform is 2a. Since it is a periodic waveform, let us try to find the function which describes the first cycle of this periodic waveform. The first cycle of this periodic waveform we denote it by the symbol f1 of t. It is a very simple function. Last class itself we have seen what is the equation to be used to synthesize a waveform of this shape. So, this f1 of t can be written as a unit step function added to delayed unit step function having a magnitude of minus 1. So, if you have a unit step function which starts at 1, and if you add a delayed unit function which is delayed in time period by a, then we get this resultant function. So, the equation for the first cycle of this square wave is f1 of t is equal to u of t minus u of t minus a. This is the equation which describes the first cycle of the waveform under consideration. Now, let us take the Laplace transform of this function which we call it as f1 of s. So, f1 of s is given by 1 by s into 1 minus e power minus as. This 1 into 1 by s is the Laplace transform of u of t, and 1 by s into e power minus as is the Laplace transform of u of t minus a. So, this is the Laplace transform of first cycle of your waveform. Once you know the Laplace transform of first cycle of waveform, we can find the Laplace transform of the periodic function by multiplying the Laplace transform of first cycle with the term 1 divided by 1 minus e power minus 2as. Listen here, here it is minus 2as because the time period of this function is not a, it is 2a. So, f of s is 1 divided by 1 minus e power minus 2as into f1 of s. But what is f1 of s? f1 of s is 1 by s into 1 minus e power minus as. So, substituting f1 of s in this expression, I can get the expression for f of s as f of s is equal to 1 minus e power minus as divided by s into 1 minus e power minus 2as. Again, to bring it to the form which is given in the question, what is asked? You have been asked to prove that the Laplace transform of this wave is 1 divided by s into 1 plus e power minus as. But what we have got? We have got the Laplace transform of the function as 1 minus e power minus as divided by s into 1 minus e power minus 2as. So, to bring it to the form which is given in the question, let us split this term. Let us split this term. So, this term 1 minus e power minus 2as can be realized as 1 square minus e power minus as whole square. This term can be realized as 1 square minus e power minus as whole square. So, I can split this term into two terms as 1 minus e power minus as into 1 plus e power minus as. In the numerator also we have a term 1 minus e power minus as. So, I can cancel out these two terms. I can cancel out these two terms, which results in the answer for f of s as f of s is equal to 1 divided by s into 1 plus e power minus as. That is what is given in the question paper. The question. Now, till now we have seen functions and we synthesized some waveforms which involves step functions. Now, let us see how to synthesize some of the waveforms which can be synthesized in terms of ramp function. So, before going to the actual synthesis, let us have a quick review of the ramp function. As you all know, a unit ramp function is defined as f of t is equal to t for time period t greater than or equal to 0 and f of t is equal to 0 for time t less than 0. Pictorially, we can represent the ramp function, graphically we can represent the ramp function having unit slope as this. This is a ramp function whose value is 0 for time t less than 0 and its value is equal to t for time t greater than or equal to 0. This is a ramp function with unit slope. So, combining these two equations, instead of writing into two equations, one for what, instead of describing the function for time period less than t naught and time period greater than t naught, we can describe these two, we can combine these two equations and we can easily write f of t is equal to t into u of t. So, when I say t into u of t value is equal to 0 for time period less than 0. So, any t multiplied by 0 becomes 0, t multiplied by u of t value is 1 for t greater than 0. So, t multiplied by 1 gives you t. So, these two equations put together can be combined and it can be written in this form, f of t is equal to t into u of t. So, if you have a function like this, the equation of this function f of t is t into u of t. And we know the Laplace transform of t u of t. Laplace transform of t u of t is given by 1 by s square. Now, let us have a ramp function which has some slope other than 1. So, let us say I have a ramp function whose slope is a by t, whose slope is a by t. We have a ramp function whose slope is a by t. How do we describe such an equation or such a function? Say, let us say f of t has a its value is a by t into t for time t greater than 0 and its value is equal to 0 for t less than 0. So, combining these two equations, instead of describing the equation for the time period less than 0 and time period greater than 0, I can combine these two equations for into one equation which holds good for any value of time t. So, I can write f of t as a by t into u of t. So, whenever I multiply any function with u of t, the function value exists only from t is equal to 0. So, that is the advantage of step function. That is the reason step function is also called as switching function. So, f of t can be written as a by t into u of t. And we know the Laplace transform of this function, since a and t are constants, f of s can be written as a by t into Laplace transform of t u of t. We know Laplace transform of t u of t is 1 by s square. So, Laplace transform of a ramp function with slope a by t is given by a by t into 1 by s square or a by t s square. Now, let us consider a shifted ramp function, because often we will be using in our waveform synthesis the ramp functions which are shifted in time. Now, look at this figure, is a ramp function whose slope is again a by t. See the basis here, if you look at the marking, magnitude of this function at this point is a against time 2t, whereas magnitude of this function is 0 when time t is equal to capital T. So, if you find the slope of this line or slope of this function is again a by t, its slope is a by t, but instead of starting from 0, this function is starting from time t is equal to t. So, it is a shifted ramp function. We know how to write the equation for a shifted ramp function. So, the equation of this function f of t is f of t into t minus t into u of t minus t. So, this is the equation of a shifted ramp function having a slope a by t, a by t. Now, let us find the Laplace transform of this function. So, this is a shifted function. So, we know by shifting theorem, Laplace transform of a shifted function which is shifted in time by an amount t is given by e power minus ts times the Laplace transform of the original function. So, Laplace transform of this shifted ramp function is e power minus ts into the slope a by t into 1 by s square, or I can write it as e power minus ts into a divided by ts square. This is the Laplace transform of shifted ramp function. Then let us find the Laplace transform of ramp function with negative slope. It is a shifted function and it also has negative slope. So, look at this figure. This is a system, this is a function, it is a ramp function whose slope is minus a by t. It is a function whose slope is minus a by t, or it is nothing but that just the negation of this function. This is a negation of this function. Since it is a negation of this function, the equation of this function f of t is minus a by t into t minus t u of t minus t. So, what is the Laplace transform of this function? Laplace transform of this function is negation of Laplace transform of this function. So, it is minus e power minus ts into a by ts square. Now, we have seen how to find the Laplace, what is the Laplace transform of a ramp function, what is the Laplace transform of a shifted ramp function, and what is the Laplace transform of a ramp function whose slope is something other than 1. Now, let us see what is the resultant function if we add two ramp functions. See here, if you look at this figure, I have two ramp functions. One is the ramp function whose slope is a by t, and it starts from t is equal to 0. So, this equation of this ramp is a by t t u of t. This a by t, a by capital T is the slope of the function. So, the equation of this first function is a by t into t u of t. Now, let us assume that I have a negative ramp function with negative slope and it is time delayed by time period t. Just now we saw in the previous slide what is the equation of this waveform. The equation of this waveform is minus a by t, that is the slope of this line, minus a by t into t minus t into u of t minus t. So, this is a one function f1 of t and another function f2 of t. f1 is ramp function with slope a by t, f2 is a delayed ramp function with a negative slope and the value of slope is again a by t. Now, if I add these two waveforms, what will be the resultant waveform? Up to that time period t is equal to 0 to capital T. During this time period, the value of second function is 0 and the value of first function is a by t into t. Value of first function is a by t into t. So, the sum of these two functions results in a function whose value coincides with the value of first function, because the second function value is 0. So, this is what I have shown in red color. This is the resultant of f1 of t and f2 of t between the period 0 to t. At this moment, that at this instant when the time period t is equal to capital T, value of first function is a, whereas value of second function is 0. So, the resultant is a. Hereafter, if you see the value of this function, this becomes a plus x, this becomes just x, because that both the, if I call at this instant of time, say at this point, if the value of this function is a plus x, this function value will be minus x. So, if I add these two together, it will be the resultant value will be a. So, if I add two ramp functions two ramp functions, then the resultant function, the slope of the resultant function is equal to the slope of the first function plus slope of the second function. So, this slope is a by t, whereas slope of the second function is minus a by t. So, if I add these two ramps having a slope a by t and minus a by t, the resultant signal has a slope of 0. So, you can see it is a straight line parallel to t axis whose slope is 0. So, in general, if you add two ramp signals of different slopes, the slope of the resultant signal is given by the slope of the ramp signals which involve in the summation. So, now coming back to the equation, now let us try to find the Laplace transform of the resultant wave. So, if I add a ramp of value, a ramp of nature a by t, t into u of t, and another ramp with the equation a by t, t minus t, u of t minus t, we get a resultant function which has a slope of a by t up to point t, and later on it has a constant magnitude which is equal to a. So, let us find the Laplace transform of this function. So, Laplace transform of this function is Laplace transform of this first component plus Laplace transform of the second component. What is Laplace transform of first component? It is a by t into 1 by s square, whereas Laplace transform of this component is a by t by s square into e power minus ts, because it is a shifted ramp function. So, if we simplify by taking out the common terms, you can write f of s is equal to a by t s square into 1 minus e power minus ts. So, Laplace transform of this waveform, which is shown in red color, is a by t s square into 1 minus e power minus ts. Now, having understood how do we generate this waveform and what is the Laplace transform of this waveform, let us see how to get the Laplace transform of a Sawtooth waveform. So, I have a Sawtooth waveform with slope a by t, Now, our aim is to get the Laplace transform of this particular function. Let us see how to generate this function. How do we synthesize this function? To synthesize this function, I can easily synthesize this function from the previous function, that is from this function. If I make the function value, if you look at this function, the value of function is a constant for time period t greater than capital T. Now, instead of having a magnitude 1, if I make the magnitude 0 for time period t greater than capital T, then I get this function. So, previous function had a straight line having a slope a by t, and later on it had a constant magnitude of value a. Hereafter it had a magnitude a. Now, if I cancel this magnitude a, if I make it 0 somehow, then we get this resultant waveform. What should we do to make this magnitude 0? The magnitude of this function after t greater than capital T is capital A. So, if I add another unit step function with magnitude minus a or negative step function, then we get this Sawtooth waveform. So, we can easily get the equation for Sawtooth waveform as, we can synthesize it as a ramp signal, then a shifted ramp signal and with a step signal. So, if I write the equation for this ramp function, I can write it as f of t is equal to a by t, t into u of t, that is the equation of the ramp, minus a by t into t minus t, u of t minus t, that is the shifted ramp with a negative slope. Then with these signals, I have to add a step function of magnitude a, which has a negative which is on the negative side. So, f of t can be written as a by t, t u of t, minus a by t, t minus t, u of t minus t, minus a into u of t minus t. Now, this is the function which describes this waveform. So, let us find the Laplace transform of it. So, Laplace transform of it is given by f of s. F of s is the sum of these Laplace transform of these individual components. So, f of s can be written as a by t into 1 by s square minus e power minus t s times a by t into 1 by s square minus e power minus t s time a by s. Hereafter it is only the simplification. So, now if you look at these two terms, a by t s square is common in these two terms. So, I can write these two terms as a by t s square into 1 minus e power minus t s minus the last term can be written as a e power minus t s by s. So, this is the Laplace transform of the Sawtooth wave. Once you know the Laplace transform of Sawtooth wave, you can very easily find the Laplace transform of a triangular waveform. So, the problem given here is, for the waveform shown, show that the transform of this function is f of s is equal to 1 by a s square minus e power minus a s divided by s into 1 minus e power minus a s. Now, our aim is to prove that the Laplace transform of this waveform is 1 by a s square minus e power minus a s divided by s into 1 minus e power minus a s. Since it is a periodic waveform, we know how to find the Laplace transform of periodic waveform. Laplace transform of periodic waveform can be obtained if we know the Laplace transform of the first cycle of the waveform. So, let us try to get the Laplace transform of the first cycle of this waveform. If you look at this waveform, it is a Sawtooth waveform whose slope is 1 by a. The slope of this Sawtooth waveform is 1 by a. So, if you write the equation for the first cycle of this Sawtooth waveform, which we call it as f1 of t. f1 of t can be obtained by adding these three signals. What are the three signals? The first signal is a ramp signal starting at time t is equal to 0 and having a slope of 1 by a. So, this f of t can be obtained by 1 by a t into u of t, which gives you this signal, and at t is equal to a, I need to add another ramp signal whose slope is also 1 by a, with a negative sign, and it should be shifted in time by a. So, the next signal which I need to add is minus 1 by a t minus a u of t minus a. And if I add these two signals alone, what will be the resultant? The resultant signal will be a ramp signal from 0 to a, and then thereafter it will have a magnitude of value 1. So, I need to cancel out that 1. So, what should I do? I need to add another step function having a magnitude minus 1. So, f1 of t can be written as 1 by a t u of t minus 1 by a t minus a u of t minus a minus u of t minus t. This gives you the first cycle of the periodic waveform. Now, once you know the equation for the first cycle of the periodic waveform, we can easily find the Laplace transform of this function. So, Laplace transform of this function, I call it as f1 of s. So, f1 of s is given by 1 by a s square minus e power minus a s 1 by a s square minus e power minus a s into 1 by s. So, this is the Laplace transform of first cycle of the periodic waveform. Again, we can simplify this function and write it as 1 by a s square into 1 minus e power minus a s minus e power minus a s into s. So, this is the Laplace transform of first cycle of the waveform. But what do we want? We want the Laplace transform of the entire waveform. So, Laplace transform of the entire waveform f of s is given by 1 by 1 minus e power minus a s time the Laplace transform of first cycle of the waveform. So, it is 1 by 1 minus e power minus as times this function, this f1 of s. So, this is the Laplace transform of the periodic function. So, if you multiply this term with the first term, so inside the bracket we have two terms, if I multiply these two terms, this term results in, the product of these two terms results in 1 by a square, and the product of these two terms results in e power minus as divided by s into 1 minus e power minus as. That is what we have been asked to prove. So, that was the expression given in the question. So, hence we could get the Laplace transform of a triangular wave whose which has a time period of a, and slope of the Sawtooth wave is 1 by a as 1 by a s square minus e power minus as divided by s into 1 minus e power minus as. Now, let us consider a triangular waveform. So, now till now we took an example of Sawtooth waveform. Now, let us consider a triangular waveform. So, let us say my aim is to synthesize this triangular waveform. So, it has a peak value of a, and let us say how do we synthesize this. If you look at this triangular wave, the slope of this segment is unity, because its peak value is a and its x axis value is also a. So, this beginning part, this part has a slope a. If you look at this segment, again if you see the slope, it has a negative slope of again value unity, because here the change in t axis value is a and its peak value is a again. So, the slope of this segment is minus 1, the slope of this segment is plus 1. Now, so let us try to write the equation for this one particular cycle of triangular wave. How do we do it? So, here to get this segment, we can get this segment easily by having a ramp signal of slope unity. Now, as I told you in the beginning, when you add ramp signals, the resultant signal, the slope of the resultant signal can be obtained by adding the slopes of the two ramps which are involved in the summation. Now, the slope has to change from plus 1 to minus 1. The slope has to change from plus 1 in this segment into minus 1 in this segment. So, if the slope has to change from plus 1 to minus 1, I need to add a ramp whose slope is minus 2. If I add a ramp with a slope minus 2 from this point t is equal to a, if I add a ramp with a slope minus 2 from this point t is equal to a, then the resultant signal will have a slope of minus 1. So, the function can be written as f of t is equal to t into u of t minus 2 times t minus a u of t minus a. So, if I add these two signals, what will happen? This signal will have a segment which varies from 0 to a, we will get this segment, and this segment will continue even after 2a, but I want the value of the function to be 0 after 2a. So, this is a ramp which has a negative slope, and it is and its slope is 1, or I can say this ramp will continue, this ramp with a slope minus 1 will continue even after time period t is equal to 2a, but our aim is to make its magnitude 0. So, what should I do? To make this negative ramp 0, I need to add another ramp at this point 2a, whose slope is plus 1, So, first I should start with a ramp with positive slope of value 1, then at this instant of time I need to add another ramp with slope minus 2, and again at this point I need to add a third ramp signal whose slope is again 1. So, if I put it in equation form, I can write f of t is equal to t into u of t minus 2 times t minus a u of t minus a plus t minus 2a u of t minus 2a. So, this is the equation which describes this function. So, now let us take the Laplace transform of this function. So, Laplace transform of this function, we call it as f of s. F of s is Laplace transform of this function, that is t u of t, which is given by 1 by s square, minus Laplace transform of this shifted ramp, which is given by e power minus as 2 by s square, plus Laplace transform of this third ramp function, that is given by e power minus 2 as into 1 by s square. So, we can simplify by this term because all these terms have s square in the denominator. So, we can write f of s is equal to 1 by s square into 1 minus 2 e power minus as plus e power minus 2 as. Again, this is of the form 1 square plus e power minus as whole square minus 2 into 1 into e power minus 2 as. So, I can write this function as 1 minus e power minus as whole square. So, Laplace transform of this waveform is 1 by s square into 1 minus e power minus as s square. Now, let us take a trapezoidal wave which involves in its synthesis both ramp function and some step function. So, let us see how to get the Laplace transform of this particular trapezoidal wave. So, if you look at this wave, to start with, if you see this segment of the function between the time period 0 to t, it is a ramp function whose slope is 1. It is a ramp function whose slope is 1. Then from time period 1 to 3, the slope is 0, and magnitude of this function is 1. And from time period 3 to 4, again it has a negative slope and slope is 1, or I can say the slope of this segment is minus 1. Here slope is 1, slope is 0 and slope is minus 1. So, very easily you can write the equation of this waveform. To start with, I need to have a ramp with slope 1. So, we start the synthesis with ramp with slope 1, which I can write it as t into u of t. So, equation of for this segment is t into u of t. But at time t is equal to 1, at time period t is equal to 1, the slope should change from plus 1 to 0. The slope should change from plus 1 to 0. If the slope has to change from plus 1 to 0, at this time instant, I need to add a negative ramp or ramp with a slope of minus 1. I should add a ramp with a slope of minus 1. So, to make this magnitude constant, to make this magnitude equal to 1, that is to make the slope 0, with this t u of t, we add a signal given by t minus 1 u of t minus 1. So, if we at all we have only these two signals, then our function will have a ramp up to 1 and thereafter it will be a signal having a magnitude of value 1. It will continue like this, but we do not want it to continue with the magnitude 1. At time period t is equal to 0, we want the slope to change from 0 to minus 1. 0 to minus 1 at time period t is equal to 0. This is achieved by adding another ramp signal with slope minus 1 at time period t is equal to 3. Time period t is equal to 3. So, if I just leave it at this point, even after time period t is equal to 4, the ramp will continue along the fourth quadrant, or it will continue in this fashion. It will continue here. What should I do? So, there is a ramp with negative slope, minus 1 slope. I want to make it to 0. So, I need to add another ramp with positive slope. So, if I combine all these concepts and write the equation, I can write f of t is equal to t into u of t minus t minus 1 u of t minus 1 minus t minus 3 u of t minus 3 plus t minus 4 u of t minus 4. So, we can take the we can easily find the Laplace transform of this expression. So, Laplace transform of this expression is given by f of s is equal to 1 by s square, because all these signals are ramp signals. All these signals are ramp signals. So, all these terms will have s square term in the denominator. So, I can easily write 1 by s square into 1 minus e power minus s corresponding to this term minus e power minus 3s plus e power minus 4s. So, this is the Laplace transform of this waveform. Now, let us try to find the Laplace transform of a signal like this. It has a, look at this signal, it has one segment with slope 1, and this segment also has the slope 1. This is also having, this segment also has a positive slope of 1, even this segment has positive slope of 1, and again finally it becomes 0 after t is equal to 3. So, let us see how to synthesize this waveform. To start with, I need to have a ramp signal. I need to have a ramp signal having a slope 1. So, we need to have a signal t u of t. But if you look at this second segment, the slope of the first segment and slope of the second segment are same. So, the signal which I need to add should have 0 slope. So, just in the beginning I told you, if you add two ramp signals of slope say x1 and x2, the resultant signal slope will be x1 plus x2. So, now this has a unit slope, here also I have unit slope. Without disturbing this signal, if I would have just left this signal would have continued like this. The signal would have continued like this. At time t is equal to 2, its value will be 2. At time t is equal to 3, the signal value would have been 3. But at time 2, the signal value, original signal, if I without disturbing, if I leave it, it will have the value 2, but I want to make it 0. So, what should I do? This 2 has to be cancelled with minus 2 to make it 0. At 3, if you see, if I would have left the signal as it is, it would have reached the value 3 plus 3, but I want to make it 1. So, plus 3, if I want to make it plus 1, I need to add minus 2. So, even at this instant, I need to add a magnitude of minus 2 to the original signal. Here also I need to add a magnitude of minus 2 with this signal, or I can easily write, to bring this signal from this segment to this segment, I need to add a step function with magnitude minus 2. If I add a step function with magnitude minus 2 at this time instant, this signal will change, this ramp which is continuing like this will be pulled down, it will be pulled down. So, f of t is equal to t into u of t minus 2 u t minus 1 gives me this signal. But again what do I will have? This is, the signal is continuing as a ramp, this will continue as a ramp. So, I need to change the slope to 0 and then make the value also to become 0. So, I need to do two manipulations at time t is equal to 3. So, to bring down this, to cancel out this ramp, I need to add another ramp with same slope, that is unit slope. If I add another ramp with unit slope, this ramp will continue with this signal will continue, it will be a constant signal with magnitude 1. But to cancel that magnitude 1, I need to add another step signal with magnitude minus 1. So, I need to bring the signal to have a change at time t is equal to 1, we are adding a unit step signal, and to bring down the signal value to 0 at time t is equal to 3, we need to add a ramp signal and step signal. So, f of t is equal to t u of t minus 2u into 2 u of t minus 1 minus u of t minus 3 minus t minus 3 u of t minus 3. So, Laplace transform of this function is 1 by s square minus 2 e power minus s by s minus e power minus 3s by s minus e power minus 3s by s square. This is the Laplace transform. So, if you conclude what we have studied in today's class, we have seen how to get the Laplace transform of a periodic function. We took an example of a rectangular wave. We have seen how to get the Laplace transform of a square wave. We have also seen how to synthesize few of the waveforms which involves both ramp signal and step signal. Thank you.